All right, welcome everyone. Today we're going to continue talking about how to integrate powers of secant and tan. And unfortunately, it's not going to be super satisfying. So the substitution strategy that we looked at last time, particularly in the first two examples, doesn't always work. And so what happens is we just sort of have this kind of grab bag of techniques that we can try out, and hopefully one of these works. So the first thing we can try is just try using some trig identities and just rewriting the function that you're working with. So the main one main trig identity for dealing with powers of secant and tan is our usual secant squared theta equal to 1 plus tangent squared theta. So that might still give you something useful. Another strategy that can be helpful from time to time is converting everything into powers of sine and cosine. So we have a whole separate strategy for how to integrate powers of sine and cosine. So converting everything to them, that might be helpful. And we just want to remember, what is tangent and what is secant in terms of sine and cosine. So, it's going to be helpful to remember that tangent theta is equal to sine over cosine. So sine theta over cosine theta. And secant is 1 over cosine. It's the reciprocal of cosine. So those might be helpful to remember specifically for option 2 here, converting everything to sine and cosine. Another thing we could try is try integrating by parts. So if we have our trig integral involving powers of sine and involving powers of tangent and secant, integration by parts is nice, because it kind of moves the exponent around a little bit. And we'll see this in one of our examples today. But when you think about trying an integration by parts, what you want to do, or one possible thing to try, is making your dv term either secant squared or secant times tan. So when we're doing integration by parts, for our dv term, we're eventually going to have to integrate that. So our dv term has to be easy to integrate. And when we're talking about powers of secant and powers of tan, the only two terms here that are pretty easy to integrate are secant squared. So let's just remember what that is. That's just tangent. And I'll write the plus c. And then what about secant times tan? Well, that's just secant. So we know when we're doing integration by parts, when we choose dv, we're eventually going to have to integrate that. So whatever we pick has to be easy to integrate. Well, secant squared is one of our kind of elementary integrals. It's just tangent. And then secant times tan is also one of our elementary integrals. It's just secant. All right, so those are kind of the three things we could try. And another thing to kind of keep in mind is that there are a few other helpful antiderivatives that we might need to use. So, we kind of looked at the integral of tangent when we talked about substitution rule. You can prove this one. It ends up being the natural log of absolute value secant x. And then the integral of secant x, this is another helpful antiderivative. The antiderivative of secant x is the natural log of absolute value secant x plus tan x. Now this one really, we haven't seen how to do this one. It really involves just a trick. So we'll just kind of take this one as it is. Being able to integrate just secant x, just know that the antiderivative is natural log absolute value secant x plus tan x. So these are just a couple other helpful ones to know while we're kind of getting creative here with these assortment of other strategies. All right, so let's try an example. Let's try integrating tangent x cubed. And let's try strategy 1 here. Let's use our trig identity. See if that gets us anywhere. So we're going to use our trig identity, and let's write it down before we get there. We know our trig identity is secant squared theta is equal to 1 plus tangent squared theta, and it has a power of tangent squared. So when we look at this integral, we need to get a tangent squared. So let's break up this function a little bit. Let's write it as tangent x times tangent squared x. And again, the reason why we're doing that is the trig identity we have to work with has a tangent squared in it. So let's get a tangent squared in our function here, explicitly. All right, so now that we have that, let's plug it in. So this is going to be the integral of tangent x. And then instead of tangent squared, it's going to be secant squared minus 1. All right, so there we go. We've rewritten our integral, and that was using our trig identity. Now let's try multiplying this out and see what we have to work with. So if we multiply this out, we end up with tangent x times secant squared x minus tangent x. And the integral of tangent x, that's one of those useful antiderivatives we just mentioned. So this tangent x, that's one of our useful antiderivatives. We're going to be able to do that. So what about this tangent times secant squared? What can we do there? Well, that's going to take a little bit of work, but we're going to be able to use our usual strategy. We have an even power of secant here. So even powers of secant are always nice. And then that tangent x, that's one of our kind of our useful ones that we're going to be able to do something with. All right, so as it stands, we're going to be able to do something with this tangent x that's by itself, but we're also going to be able to do something with this tangent x times secant squared. So let's work with this one first. And we'll just kind of do these separately off to the side, and then we'll kind of put our results together. So let's look at the integral of tangent x times secant squared x dx. And we have this even power of secant squared, so we know that we can kind of reserve that, put it next to the dx and keep that reserved. And then we can just do a u substitution. So we have this even power of secant squared next to our dx. That's going to become part of our new differential once we do the substitution rule. And then everything else here, we want to convert to tangents. And the reason is because then we can just do a nice substitution rule where we let u equal tangent x. What's the derivative of tangent? It's secant squared. And so the tangent here, that's going to become u. And then the secant squared x dx, that's going to become our differential du. So this ends up just becoming u du once we plug in all our pieces. And the antiderivative of u, that's just basic power rule. So what is it? It's 1/2 u squared. And we'll save plus c until the very end. And then we convert back. So we plug in tangent. I'm running out of room here, so I'll just write this here. 1/2 tangent squared x. There we go. So we found the antiderivative of this tangent times secant squared. It's 1/2 tangent squared x. What about the antiderivative of this tangent term? Well, we're going to be able to just refer back. So let's fill in what the antiderivative of that we found for this tangent times secant squared is. We found it was 1/2 tangent squared. And then what about that tangent x? Well, let's just go back to our helpful antiderivatives. And there we go. The integral of tangent x is natural log of absolute value secant x. And then we put our plus c. So there we have it. So we were able to, we had this odd power of tangent, but there were no other secant terms. So normally what we would do if we had an odd power of tangent is we would take one of the tangents, we would take a secant and put it next to the dx. Now the issue, why couldn't we do that here? Well, we don't have a secant to really work with. So instead, we kind of broke off a tangent squared, used our trig identity, and then that was able to kind of convert things into two integrals that we could do. And then we were able to get our answer. So that's kind of one technique, is try out using the trig. If you get stuck on one of these powers of secant and tan, just try using the trig identity and see where that gets you. Let's try it a different way. Let's try it now with powers of sine and cosine. So we're going to try this one. And we're going to just convert everything to sine and cosine. So what is tangent x in terms of sine and cosine? Well, it's sine over cosine. So this integral, if we're going to convert, is going to be sine cubed over cosine cubed. So what we've done there is we've converted into powers of sine and cosine. And we have a whole strategy that we developed for how to handle powers of sine and cosine. And what we see here is we have an odd power of sine. So that's always nice. What we can do is we can peel off one of those sine terms, put it next to our differential. And that'll give us a sine squared on top. We'll still have our cosine cubed in the denominator, but now we're going to take one of the sines in our sine cubed, and we're going to put it next to the dx. And so we're reserving that for a u substitution. So let's think, if that's going to become our differential, let's kind of work backwards to figure out what the u substitution is going to be. So if sine x dx is going to become our differential, how do we get sine? Well, we get sine by letting u equal the other one, letting u equal cosine. And so when we differentiate, when we choose u equal to cosine, derivative of cosine is negative sine x, and then dx. And that's a pretty good match for our substitution. The only thing here is we have this extra negative. So what can we do? Well, we can divide both sides by -1. and that'll give us, well, or we can just multiply both sides by -1. And that just gives us -1 times du is equal to sine x dx. And now we see that this is going to match up perfectly with what we have actually in our integral. So we're going to want to go through and convert everything here. And we're going to be letting u equal cosine. So that means everything in the rest of our integral here, all of these extra terms, we have to convert into cosines. So we want to convert everything here to cosine terms. And we know we have a trig identity that allows us to do that. So this sine squared, we have our usual sine squared plus cosine squared is equal to 1 trig identity. So we end up with the integral of 1 minus cosine squared x all over cosine cubed x. And then we still have our sine x dx there at the end. And we're saving that. We don't have to convert that. We know what's going to happen to our sine x dx there. It's going to become part of our new differential. And so now we're ready to just kind of fill in all the pieces. So we know the sine x dx, kind of by design, is going to become our differential. So -1 times du. And then wherever we see a cosine here, that's going to become u. So we're going to end up with 1 minus u squared divided by u cubed. So when we do that, we get 1 minus u squared over u cubed, and then times our -1 du. And so there's our nice integral, and we've gone through and substituted in all of the pieces here. So now let's start integrating this. Let's distribute the negative. So we can take that -1 and bring it into the numerator just to kind of clean things up a little bit. And then while we're at it, let's actually do the division. So let's split up these into two separate fractions. So we're going to end up with u squared over u cubed, which will just be 1 over u. And it's going to be a double negative, so let's just write it as a positive. And then when we bring the -1 to this one term in the numerator, that'll be divided by u cubed, so we're going to end up with 1 over u cubed. So just kind of combining a few algebraic steps there, we end up with, simplifying this down, we end up with 1 over u minus 1 over u cubed. We wanted to get these really as kind of two separate pieces because now we can these are just elementary form integrals that we can just do. So what's the antiderivative of 1 over u? It's just natural log absolute value u. What's the antiderivative of 1 over u cubed? Well, that's power rule. So it ends up being u to the -2. Take that new exponent, flip it, put it in front. So we end up with plus 1/2. Ends up being a double negative, so it becomes positive 1/2. And then we add c at the very end. And then the very last thing we need to do is just convert back to x. So we have our antiderivative here, and we just want to convert back to x. So we're going to get natural log of absolute value cosine x plus 1/2 cosine raised to the -2x plus c. Now, you might be wondering, if we look at that, that's a perfectly good answer right there. But if you're looking at that, it might look a little different than the version we found over here. And you can work with it. It might be good practice to see that these are actually equivalent antiderivatives. So, we know, going over here, we know secant is 1 over cosine, and we have a log property that lets us handle division inside of the log function. And then we also have an identity that allows us to convert back and forth between tangent squared and, well, cosine x raised to the -2. That's the reciprocal of cosine squared. So that's going to be a secant squared here. So there's a little bit of kind of fun you could have by just using some log properties, using some trig properties, and you should be able to see that these two antiderivatives that we have, they look very different, but they're actually equivalent. All right, let's try one more. Integral of secant cubed, just to see all the kind of different techniques that we could try. All right, so we have secant cubed, and we're going to be integrating it. And what we can try for this one, what we're going to do is integration by parts. And so usually, if we have powers of secant and we're kind of getting stuck, integration by parts tends to be helpful, especially for powers of secant. So how can we kind of start ourselves off with an integration by parts here? Well, we know we're going to we need to choose u and we need to choose dv. And when we choose dv, we want to pick something that's easy to integrate. So, when we have powers of secant and powers of tan, really we have two choices for what we could pick for dv that's easy to integrate. We could either do secant squared or we could do tangent times secant. I don't see any tangents here, so let's kind of break this apart. We're going to break off a secant squared. We're going to write this as secant x times secant squared x dx. And secant squared, that's one of our elementary form integrals. That's one of our basic ones. So that's what we're going to pick for dv. And so if this is all going to become dv, then our choice for u has to be anything that's left. So u is going to equal secant. So that's our choice. Let's see if it works. So we're going to calculate du. So the derivative of secant is secant times tan. The integral of secant squared, and this is kind of why we picked it, the integral of secant squared is just tangent. So that was not too bad. And then we apply our integration by parts formula. So let's just remember what that is. It says the integral that we're trying to do is u times dv, and it's equal to the integral of u times v, so secant times tan, minus the integral of v times du. And I'm forgetting my dx here, so let's make sure we put that in. So we're going to do minus the integral of tangent times secant times tangent dx. So we're going to end up with secant x tan squared x. And we're going to keep going with the integration here. So let's keep going. And we have this tangent squared. Now when we look at the formula here, we're done with this part, the secant times tan. Then we have minus this integral of secant times tangent squared. And we have to do something with this remaining integral. The issue is it's a power of secant and tan. It doesn't have an even power. Doesn't have an even power of secant, so that's something we can do. And it doesn't have an odd power of tangent. So that's also an issue. Generally, if we have an even power of secant, we can kind of use our original strategy. If we have an odd power of tangent, generally we can use our usual strategy of substitution rule. But we don't have either of those here. And so this is another case where we just kind of have to try things out and hope for something to work. And we have this tangent squared. So let's try using our trig identity to convert that into, well, see what happens, I guess. Let's just try using our trig identity and see what happens. So we're going to let tangent squared x equal secant squared x minus 1. We're just going to try our trig identity here. And hope for something to work. So we've converted this from an odd power of secant. So, we really are good. We can handle even powers of secant. Odd powers are things get a little bit trickier. So that kind of motivated the whole let's try integration by parts. Doing integration by parts converted everything into a new integral. But we're still having some difficulty with this new integral. It's not an even power of secant. It's not an odd power of tangent. So then we try one of our other strategies. So just try using a trig identity and see what happens. So we're going to convert that tangent squared x into secant squared minus 1. So let's fill that in. And when we do that, we're going to get this part we're done with. So secant x times tangent x. And then we're going to have, let's fill in the trig identity here. So we're going to have minus the integral of secant x times secant squared x minus 1 dx. And, I don't know. Let's multiply that out and see what we get. So we're going to have secant times tangent. And then we're going to have minus the integral of, let's actually distribute this. So we're going to have secant times secant squared. So that's going to give us secant cubed. And then minus secant. And, well, it looks like we're back where we started. So we have integral of secant cubed here. That's the one we're trying to do. We did all this work. We're kind of going in circles, it feels like. We did integration by parts. We got this integral of that we still couldn't do really. Or at least we didn't have a real strategy for doing. So we tried a trig identity. Plugged in the trig identity, multiplied things out, and now we're back to having an integral of secant cubed. But we've seen these kind of before when doing integration by parts problems. So sometimes if you do integration by parts enough, the integral you're trying to do, or the integral that you want, kind of shows up on both sides of the equation. So let's rewrite this equation now with everything that we've found. We found that it's equal to secant x times tangent x minus the integral of secant cubed x. And I'm going to break that integral up. So I'm going to break this integral up. We're going to have minus secant cubed x and then plus the integral of secant x. And when we look at this, we've done a whole bunch of things, and we're kind of back where we started, but we have that trick, that algebraic trick that says, all right, we We don't know what this integral is. We have this equation. We know it's all true. Everything we've done is correct. The integration by parts is fine. Using that trig identity is fine. So this equation is true. We still have a few integrals to do, but we know this equality is true. And then we also see our unknown integral right here. And so we can treat this as more of just like an algebraic problem. We have to solve for this unknown integral. So we're going to take that negative secant cubed integral over here, and we want to move it to the other side. So we want to get rid of this. So how are we going to get rid of it? Well, we're going to add it to both sides. So think of it as we're going to add the integral of secant cubed x dx on this side, and that'll cancel it off. And then we're going to add the integral to this side. Now, when we add two unknowns, we just add their coefficients. So both of these integrals kind of have hidden coefficients of 1. So we're just going to add their coefficients together. And that'll give us 2. We have 2 copies of secant, the integral of secant cubed there on the left. And this is going to be equal to secant x tan x. We're done with that piece. Plus the integral of secant x dx. And we were able to get rid of this one. We were able to cancel it off. So we moved it to the other side. That's why we have 2 copies of this integral now. And this is still our unknown integral. So that's what we want to solve for. So we're solving for this integral of secant cubed. So let's get that 2. Let's move it to the other side. And the way algebraically to do that is we divide both sides of this equation by 2. So we're going to end up with the integral of secant cubed x dx, the one we're trying to do. And if we divide everything on the right by 2, we're going to end up with 1/2 secant x times tangent x plus 1/2 times the integral of secant x dx. So we just divided everything by 2. And the integral of secant x, that's one of our helpful ones. So this is one of our helpful antiderivatives. So sometimes if you do integration by parts enough, you'll kind of take this higher power of secant, and eventually you'll kind of work your way down so that you end up with just an integral of secant. So we just want to refer back to, where was it? It was right here. Our helpful antiderivative. The integral of secant is the natural log of absolute value secant plus tangent. So we're just going to fill that in. And when we do that, we're done with this first part. We have our plus 1/2, and then we're just filling in that the integral of secant is the natural log of absolute value secant plus tangent. And then we have our plus c. So, you know, it takes a little bit of work to get there, and it's not so clear-cut, all the different twists and turns that you're going to have to take when you're doing these integrals. So, you know, you just try different things and see what works. So, you know, unfortunately, there's no real satisfying answer. If our usual substitution strategy doesn't work for the integral involving a power of secant or tangent, if we have an even power of secant, we can use our regular strategy. If we have an odd power of tangent with a secant term thrown in there too, we can use our substitution rule. We can use our substitution rule strategy. But where things get a little dicey is if the power of secant is odd or the power of tangent is even, things get a little difficult. So, we try integration by parts. Maybe that'll do something for us. Maybe we try using our trig identity. Secant squared is equal to 1 plus tangent squared. Maybe we try just converting everything into powers of sine and cosine. Maybe that does something for us. So sometimes you have to try just different things, and eventually you'll kind of simplify or manipulate things enough where you'll get to a point where you have something that you recognize. So you have something like the integral of secant, or you have something like the integral of tangent. Something that's still a little tricky to do, but you know what it is. All right, so we're going to stop there. So not exactly a satisfying conclusion for our powers of secant and tan, but it's good enough. We have enough tools now where we should be able to integrate most of the, no trick questions. You'll be able to integrate all of the ones that we're going to look at. But there might be some difficult ones out there. So, we have these strategies, and it should be enough, but powers of secant and tan things can get a little dicey. All right, so next time what we're going to be looking at is we're going to take all of these trig integrals that we've been looking at. There's a reason why we've been looking at them, and we're going to use a lot of these trig integrals for our next topic, which is going to be trigonometric substitution. So all of these trig identities, or trig integrals, we're going to get a whole bunch more practice with. And we'll see that starting next time. All right, we'll see you all then. Bye-bye.